So let's move now to the next part of our discussion on force and motion. In particular, we look at force analysis. In our discussion of motion along a straight line, we showed that depending on the acceleration experienced by the object will undergo different types of motion. If the acceleration is constant at 0, the object is undergoing uniform motion. If the acceleration is constant at a non-zero value, the object is undergoing uniformly accelerated motion. And if the acceleration is not constant, the object is undergoing non-uniform acceleration. Now, our discussion of Newton's laws of motion showed that there is a relationship between force and the acceleration experienced by the object. For constant mass, the net force experienced by the object is equal to mass times acceleration, which means that depending on the net force experienced by the object will undergo different types of motion. Let's look at first the first condition of equilibrium. If the net force is equal to 0, the object is said to be in a state of equilibrium. The object is said to be in equilibrium state. F net is equal to 0, which means that the acceleration is 0, the velocity is constant. A system in a state of equilibrium, therefore, will have constant velocity. If the velocity is 0, the object is in a state of static equilibrium. But if the velocity is constant at a non-zero value, the object is undergoing uniform motion. But if the net force is not equal to 0, the object is not in a state of equilibrium. F net is not equal to 0. The acceleration is not equal to 0. The velocity is not constant. A system, therefore, that is not in a state of equilibrium is characterized by a changing velocity. The system is said to be an accelerating system, and net force is equal to mass times acceleration. Again, this is for constant mass. So, depending on the net force, the system will either be in equilibrium state or it will be an accelerating system. By analyzing the net force experienced by the object or system, we are able, therefore, to analyze the motion of the object. In doing net force analysis, it pays to do it step by step, so please take note of the following steps. 1. Draw the system if no drawing or diagram is provided by the problem. If the problem or situation already provides a drawing of the system, you move on to step number 2. Number 2, identify the forces present in the system. Is there weight, tension, friction, and so on in the system? After you have identified the forces present in the system, number 3, you draw the free body diagrams or FBDs for the problem. And then number 4, you analyze these free body diagrams. You either use net force is equal to 0 or net force is equal to MA, depending on the system being described by the problem. And of course, net force is a vector quantity. Therefore, in analyzing net force, summation of all the forces acting on the system, remember to use your component method. Remember to use your vector analysis. So we illustrate these steps in terms of the following problem. So consider the following problem. An object of mass 5 kilograms is suspended by 3 strings as shown in the figure. The tension in the left string is 23.1 newtons. Determine the tension in the middle string. So in terms of our net force analysis steps, number 1, draw the system if no drawing or diagram is provided by the problem. Here we see that the drawing is already provided by the problem. So we move on to the next step. Step number 2, the next step, we identify the forces present in the system. The object is suspended by 3 strings. The object has mass m is equal to 5 kilograms. Therefore, the object has weight. Weight which is vertically downwards. Because of the weight, the 3 strings that are holding up the object are being stretched. Therefore, each string has its own tension. The strings react to being stretched by producing tension. So you have tension in the left string, tension in the right string, and tension in the middle string. Let the tension in the left string be T1, the tension in the middle string be T2, and the tension in the right string be T3. So you have T1, T2, T3, and of course, weight W of the object. The problem is looking for the tension in the middle string, so we are looking for T2. Next, we draw the free body diagrams or FBDs. We identified T1, T2, T3, and weight, so we draw these vectors or forces separate from the drawing of the system, so we can concentrate on just analyzing these forces. So you have the following vector diagram: T1, T2, T3, and you have the vertically downward weight. 45 degrees between T1 and T2 according to the diagram, and 45 degrees between T2 and T3. After we have drawn the free body diagram, in this problem there's only one free body diagram. We analyze the free body diagrams using either Fnet is equal to 0 or Fnet is equal to MA. Now, looking at the problem provided, or the situation provided by the problem, the object is simply hanging from the T strings. So the object is stationary. The object is in static equilibrium. The object is in equilibrium state. Therefore, Fnet is equal to 0. So Fnet is equal to 0. Fnet, by definition, is summation of all the forces acting on the object. So the forces acting on the object are T1, T2, T3, and weight, W. Therefore, Fnet is equal to weight plus T1 plus T2 plus T3. Therefore, 0 is equal to weight plus T1 plus T2 plus T3. And we use component method to analyze this equation. So looking at the x component first, Fnet x is the x component of Fnet. X component of 0 is still 0. Weight is vertically downwards, therefore the x component of weight is 0. T1 is 45 degrees to the left of positive y. The x component of T1 therefore is negative T1 sine 45. T2 is just like weight. It is vertical, so it does not have an x component. And T3 is 45 degrees to the right of positive y. So the x component of T3 is positive T3 sine 45. Therefore, F net x is equal to 0 minus T1 sine 45 plus 0 plus T3 sine 45. This tells us that T1 and T3 are equal, or they have the same magnitude at least. Since we already know the magnitude of T1, that means we also know the magnitude of T3, 23.1 newtons. We then go to the y component. So F net y is the y component of F net. Y component of 0 is still 0. Weight is vertically downwards, therefore the y component of weight is negative w. Y component of T1 is positive T1 cosine 45 degrees. T2 is positive y direction, vertical, therefore y component of T2 is positive T2. And y component of T3 is T3 cosine 45 degrees. This gives us F net y is equal to 0 is equal to negative w plus T1 cosine 45 plus T2 plus T3 cosine 45. Now, weight W, magnitude is just mg. So we have negative mg plus 2T1 cosine 45 degrees plus T2 is equal to 0. Here we have already combined T1 and T3 because in the x component, we found that magnitude-wise, T1 and T3 are equal. Knowing T1, knowing M, the only unknown is the magnitude of T2, so we isolate T2. T2 is equal to mg minus 2T1 cosine 45 degrees. Plotting in the values, the known values into the equation, we are able to get the magnitude of T2, which is the tension in the middle string, what the problem is asking for us to determine. T2 is equal to 16.332 newtons. And that's it for now. In the next video, we'll look at a few more examples for force and motion. Thank you for watching.